Welcome to the third video in SL8. In this video, we'll be discussing the dynamic structures of sugars. So to get us started, we'll look at a structure that we've seen a few times before. This is D-glucose, so a specific enantiomer of an aldohexose. And so it turns out if you take this structure and you analyze it by spectroscopic methods, maybe NMR or IR, you see something a little bit surprising. So what I'd like for us to do to get started and warmed up here is to predict what kinds of peaks you would see in an IR of D-glucose. So kind of where on the x-axis you'd see peaks and what functional groups within glucose you'd expect those to correspond to. So once you have a hypothesis, I'm going to actually include an IR spectrum of glucose into the video, and you can check your hypothesis against the experimental data, and then we'll reconvene. So go ahead and pause your video now and make your predictions. Okay, so now that you have your predictions, I'm going to display the IR spectrum of D-glucose measured on an instrument very similar to what you might have used at LMU. So once you see that spectrum, you can pause your video and compare your hypothesis about what you should see for D-glucose in this structure versus what you do see in IR. One of the things you may have noticed is the conspicuous absence of any type of signal in IR that corresponds to the carbonyl that's in D-glucose. We should expect to see a signal around 1700 inverse centimeters, and there's nothing anywhere near that, which tells us that whatever actually D-glucose's structure is, like when we work with it, it must mostly or entirely not actually be this form. And that turns out to be true. D-glucose, as we've written it, actually exists primarily in two different structures that are quite different from what we've drawn. And these are all in equilibrium with one another. So this, what we're going to call open chain or acyclic form of the sugar, is also in equilibrium with a cyclic form, which has a six-membered ring, where one of the atoms of the ring is an oxygen. So this is not a cyclohexane, even though it does adopt a chair conformation with many alcohol groups, which is consistent with what we know about the structure of glucose. So this structure here we're going to call a cyclic form, meaning that it contains a ring. And it turns out that it's an isomer of D-glucose because its molecular formula is the same. So you could count carbons, 1, 2, 3, 4, 5, 6, and you find 6 carbons, just like we did in D-glucose. You could count oxygens, 1, 2, 3, 4, 5, 6, and you find 6, just like we did in D-glucose. And you could count hydrogens as well, and you'd find 12, just like we did in D-glucose. So we know that this must be very similar to D-glucose. Where did it come from? Well, if we actually look at the structure here, one of the things that we notice is that the carbonyl's gone, but we can use oxidation levels to figure out where it went. So unless this is some kind of a redox reaction, which seems unlikely if this is an isomer, then my carbonyl carbon is at the +2 oxidation level, and I should find another carbon in the cyclic form of D-glucose that actually has a +2 oxidation level, and if I look carefully, I find that it's here. That carbon appears to be at the +2 form, and if I look even more carefully at that carbon, I notice that it's actually a hemiacetal. Which is a functional group that we know about. So what's left for us to do then is to figure out, well, how did we form a hemiacetal to form a ring? And I know that if I'm forming a ring, that the nucleophile and the electrophile of some kind of a bond-forming process have to be in the same molecule. And when they reach around to find each other, they form a cyclic structure. So I need to figure out which atom is electrophilic and which atom was nucleophilic to form this cyclic structure. I probably could guess that the carbonyl carbon is my electrophilic site. And that makes some sense because it looks like I'm forming a new CO bond, this one here, to form the ring. So now I need to find where this oxygen was. And to do this, I can actually use some numbering to figure out which carbon this oxygen is attached to as I go down the chain. So remember, for these open chain forms, our carbonyl carbons are going to be the lowest number we can give. So this will be 1, 2, 3, 4, 5, and 6. And so I can use that same numbering scheme on this cyclic form. But I need to figure out where carbon 1 is first. And I'm going to use the oxidation level and the fact that I know that aldehydes can form hemiacetals when they react with alcohols to help me do this. That means that the circled carbon we're going to call carbon 1. It's a little busy, I know, so that's carbon 1. And then we're going to go ahead and count around the carbon chain. So that means that we're going to go to this carbon here is 2, 3, 4, 5, and 6. As the sixth carbon is actually outside of the ring. So if I look at my numbering, the oxygen that's formed a new bond to carbon, the one I've shown in red, is attached to carbon 5. And so now when I go back to my structure of D-glucose, I can see that carbon 5 has an OH group, which should be nucleophilic. And that means that this oxygen can actually add to the carbonyl in a reaction we've seen before with smaller kinds of alcohols. So this is no different from a hemiacetal formation that you saw in SO7. But in this case, what we're seeing is that we're using an alcohol from within the same structure that contains the aldehyde, and that forms the ring. So one question you might have is, well, there's lots of alcohols here. Why couldn't other ones act as nucleophiles? And that's a good question. But we need to do a thought experiment about the sizes of rings that we form if we used alcohols from different parts of the D-glucose structure to form a ring with carbon 1, or the aldehyde carbon. So if I use the oxygen attached to carbon 2, I'm going to make a ring where I have oxygen, carbon, or a 3-membered ring, which should have a lot of strain. And that means that the hydration, or the addition product, is not going to be highly favored. And that means that this addition reaction is going to just go backwards. So as soon as the D-glucose does that to make a 3-membered ring, the ring just opens back up to the open chain form, which is far more stable. So it happens, but it's reversible and highly unfavorable. We can think about the same thing for carbon 2. This oxygen acts as a nucleophile. It's going to make a 1, 2, 3, 4-membered ring. Same problem. Lots of strain. That reaction is super unfavorable, and we don't observe the products that come from it. Carbon 4, I'm going to have 1, 2, 3, 4, 5 atoms within my ring, or a 5-membered ring. Now this is feasible, and in fact there are some sugars that form these 5-membered rings in addition to the 6-membered rings that we're seeing with glucose, but that's not universally true. And for glucose, those forms are a little bit less favorable thermodynamically, so we tend to observe only the reactions where the oxygen of C5 adds to the carbonyl, making the 6-membered ring. Okay, so you might also wonder, well, how is it that when this addition reaction happens, I get specifically this configuration at C1? So why is this alcohol pointed axial down and not some other direction? And that's a great question. It turns out that you get 2 different products from this alcohol acting like a nucleophile. This is one of them, but even though I make the same kind of new CO bond, I could actually place this alcohol in a different position. So rather than it pointing down, I can make it point equatorial up. So basically I'm going to make 2 different configurations of the center that we're making tetrahedral because of this addition. So I'm going to draw in all my alcohol groups first, and then I'll deal with that position we're talking about. So this would be the other possible product. Still a hemiacetal, still at the +2 level, but different from this product. So to make sure that we can talk about what's different between this structure and this structure in a concise way, we're going to use language about stereochemistry, because that's really the only difference between this structure and this one. And if I look very carefully, one of the things I notice is that everywhere around the ring, except for at this particular carbon, carbon 1, and carbon 1, it looks to me like my stereochemistry is the same. So we actually have 2 structures that differ in only one stereocenter out of many. And to me, that sounds like these 2 structures are epimers. And that's true. They're C1 epimers. But it turns out that the chemistry at carbon 1, because it's at the C+2 oxidation level, is really distinct from all of the other carbons in these structures. And so we give the carbon number 1 a special name. So we call C1 the anomeric position. We also sometimes call it the anomeric center. We can use those terms interchangeably. And like I said, it has distinct chemistry from every other carbon. We're going to look more at specific examples of this distinct reactivity of the anomeric position in video number 4. Okay, so we've introduced this new concept of the anomeric position, and the last thing that I want to do then is to illustrate how important this is. We actually don't even call these compounds epimers. We call them anomers. So we can say that structures that differ only at the anomeric position are anomers rather than epimers. So word on why I just wrote all this down without speaking. As you know, I've been struggling with a cough and such, and it's been coming back, so it's difficult for me to record and speak for long periods of time. So I'm building positions into this video where I can rest my voice. So we can think about this idea of anomers relative to epimers using a Venn diagram. So last time we met, we discussed the difference between diastereomers and epimers. Right, diastereomers are that some but not all of my stereocenters are opposite or changing, going from one structure to another. Epimers is a situation where I've got one position of stereochemical difference out of many possibilities. And anomers are even more specific. Now I'm actually prescribing where that stereochemical difference has to reside at the anomeric position. So anomers goes entirely inside epimers. So generally speaking, we want to try to choose the term that is most descriptive. So while it would not be wrong to say that like these two structures are diastereomers, the best thing we could do is describe them as anomers. Because that's the most specific way I can describe their difference. So the last thing that I want to do in this section of our video is to actually give names to these two structures. So the C2, 3, 4, and 5 stereochemical information is the same in this cyclic form as it is in D-glucose. So we still have the prefix gluc, but we don't necessarily have an open chain form anymore, so we're going to add another term. We're going to call this glucopyranose. So parts of these words we understand. The gluc was the stereochemistry, the ose is the molecular formula comparison that we did earlier in the video. And pyran tells me that I have a 6-membered ring in this particular form of sugar. So I want to be clear that like a cyclohexane, a 6-membered ring, is not a pyran. A pyran is actually a 6-membered ring that contains an oxygen. So the most simple pyran would be structure like this. So that's kind of the form that we're looking for. We can see it here. Okay, so this structure would also be gluco. Still the same stereochemistry at C2, C3, and C4, and C5. It's also pyran. And it's also ose. Still have that molecular formula. And so we need to add one more term or piece of these names to differentiate what's happening at the anomeric position. And we do that by actually using alpha at the beginning of the name, so alpha glucopyranose and beta glucopyranose. So just a word on what alpha and beta really describe. They call out the differences in configuration at the anomeric position. So alpha and beta describe stereochemistry at anomeric center. The factors that allow one to decide whether these are alpha or beta turn out to be a little bit specific, so I'm going to show them to you in this video, but really for the most part what I care about is that you know that alpha and beta are describing the anomeric position, and that if you, like for instance, maybe a reaction like took alpha glucopyranose and converted it into beta glucopyranose, that would be making its anomer. So alpha turns out to be when the alcohol, so OH of C1, is trans to the CH2 OH group on C5. Alternatively, beta, if we look at this structure, must be the situation where the OH group on C1 is cis to the CH2 OH group of C5. This is important because depending on the sugar you have, this, like we got mannose versus glucose versus idose or ultrose, sometimes the CH2 OH group is actually pointed down. And that means that, like, you know, you can't just say this OH group, every time it's up, it's beta, and every time it's down, it's alpha. That's true for some sugars, but not others. Okay, so in the next section of this video, we'll be discussing another representational form for how we can draw these cyclic structures without having to draw nice chairs. So if you're like most biochemists, you don't necessarily like drawing chair conformations of six-membered rings. Although I don't think it's that bad, you basically draw Budweiser's line. So biochemists have developed a slightly stylized and simplified version of these cyclic drawings to communicate stereochemistry and connectivity in pyranose structures, as well as other kinds of cyclic sugars that we'll see a little bit later in this video. So to illustrate how these so-called Haworth or Haworth projections are drawn, by the way, I think it's pronounced Haworth, but I've heard other pronunciations also. We can look at the two pyranoses that we've seen so far, beta glucopyranose and alpha glucopyranose, and we'll convert these into Haworth projections. So the idea here is that we're basically going to take this structure and imagine that the six-membered ring, rather than being kind of wavy, if you look at it straight on, it's flat. So we're basically going to represent a six-membered ring that's flat, and we'll kind of draw it with a sense of perspective, where we're looking at the ring and it's receding away from our plane of view. And to make sure that's really clear, if you want, you can actually color in these front bonds, make them kind of wedged, so it looks like they're closer to you than the stuff in the back. And so we know that these structures, that these rings, they're not actually planar. Remember that this is a representational system. It's not actually accurate with respect to structure. If we need to be exact about bond angles and such, we need to be drawing chairs. And then what we're going to basically do is communicate whether these OH groups exist above or below this plane, if we imagine this is flat. And so we're going to do that with vertical lines. So this looks a little bit like a Fisher projection, but now we've wrapped it up into a ring. And so this OH group is projecting up above the plane of the ring. So we put our OH group on the top of our vertical line, and then there's an applied hydrogen, which is axial down, and that will go here. All right, so basically what we've done is described our anomeric carbon. So just to be clear, this position here is this position. This is the anomeric center. And then we're just going to go around the ring, making sure we know where to place all of our OH groups. So this carbon here would be this carbon, right? So we're working clockwise. And it looks to me like this OH group is actually pointed down. My hydrogen that's implied is axial up, so that means that I'm going to have an OH group pointed like this. Biochemists will typically also draw the HN. I think these drawings get very complicated and messy looking if we include all the hydrogens, so I'm actually going to leave them implied. I'll leave the anomeric position so you get a sense for how you could do this and how you'll see it represented in some textbooks, especially biochemistry ones. But the most important thing is the direction the OH group points. Okay, so if I look at C3 and C3, I see this alcohol is pointed up, so I'll have an OH up. C4 is C4, that OH group is pointed down, so I'll make my OH down. And then finally for C5, I have a CH2 OH group, and that actually seems to be pointed up. My axial hydrogen is going to be pointed down. And so here I'm just going to draw vertical line, horizontal line, OH. So this would be the Haworth projection of beta-glucopyranose. So we're just representing it in a different way. So we've got like a line angle drawing, or sometimes called a conformational drawing, maybe what you're used to thinking about for chairs and cyclohexanes from first semester OChem. Haworth projections are a way to communicate the stereochemistry and the structure, and it's conventional for many biochemists, whereas organic chemists will tend to use either both of these or just the conformational drawings. Okay, so what I'd like for you to do for practice, I want you to actually draw a Haworth projection now for alpha-glucopyranose. So draw the anomer of this compound, and it'll be good practice just to get you used to drawing it. Make sure you draw the 6-membered ring first. Take your time, try to make it as nice as you can, and add in your groups. So once you've done that, we'll come back together and I'll do it as well. All right, so pause your video, draw the Haworth projection of alpha-glucopyranose. So you had a chance to actually work out how you would represent alpha-glucopyranose's structure in Haworth projection form. And so now I'll do the same so that you can check your work. I'm going to start by drawing the essentially like a template, which is just the 6-membered ring that I need to represent. And I'm going to try to draw this carefully. That wasn't careful enough. I want my bonds to be flat and nicely rendered. I can do it. There we go. And I'm going to color my bonds in a little bit to give it a sense of perspective. You don't have to do this part, but I do think it's helpful because remember we're representing structure. And now what I'm going to do is focus on, since I know I'm making the anomer, just the anomeric position. That's all I need to change. And I know that the anomeric position is going to be here. By definition, in a Haworth projection, it's always going to be if your oxygen is on the top right, or if you think about this as a map of the United States, like New York, it's going to be on the far right will be the anomeric position. So here my OH group is pointed down, the opposite configuration that I have from this structure. And there we go. So I'm electing not to draw in my hydrogens that exist on carbons here. And then the rest of this I can use identically. So my OH group at C2 will be pointed down, down, C3 is up, C4 is down, and then the CH2 OH group pointed up. So what I should see if I compare my two Haworth projections is a point of difference only at the anomeric position. Remember, that's what makes these two things anomers. And it looks to me that that's true. So this is a Haworth projection for alpha-glucopyranose. So in the next section of this video, we'll be looking at other kinds of cyclic sugars besides pyrans or pyranoses. In this last section of our video, we'll be looking at other forms of carbohydrates, and in particular a cyclic form that we're going to call a furanose, which corresponds to a 5-membered ring. So what I'm showing you here is the equilibrium between the open chain form of D-ribose, so this is a sugar that we saw in previous videos, with its so-called Furanose form. So we would call this structure ribofuranose, and the furan part means 5-membered ring. So furan is a structure that looks like this. That's actually the name of this compound. And so you can see the 5-membered ring with 1 oxygen in the ribofuranose structure itself, except for there's no double bonds, so that's where this term furan comes from. It's not just arbitrary. So this is a carbohydrate. It's got the same molecular formula as D-ribose itself, and we could even actually describe what kind of anomer of ribofuranose that we made. We know there's 2 possible anomers here. By looking at the position or the relative stereochemistry of this OH relative to our CH2OH group. So these two are cis, and that means that we're looking at beta ribofuranose. Okay, so if you wanted to draw alpha ribofuranose, you would simply invert the center, so that would be where the OH group on the anomeric position is pointed down or dashed. And we could also represent beta ribofuranose in a Haworth projection, but it'll look a little bit different because now we're not showing a 6-membered ring, we're showing a 5-membered ring. So to do that, we're going to take our oxygen and we'll place it in the back so it's as far away from us as possible and show a perspective where we're looking into this 5-membered ring where these two carbons are closest to us. So we'll have, if we want to show a real sense of perspective, more thick bonds, which I'll color in. Voila. And now what's left for us to do is to add the various functional groups. So this alcohol group is projecting toward us or up from the position that would be this OH like so. So remember, in this perspective, we're looking at this ring side on, right? So it's like the ring is coming out of the board at you. Whereas in this case, we're looking at the ring flat. So if our OH group is pointed up in this perspective, and I rotate the ring to have the perspective that I'm looking at here, it's going to be OH group pointed up. Same thing is true for a dashed OH, right? That's going to be projected away from us, and then as we rotate the ring, that OH group is pointed down. So we'll add our OH here. Same thing for the next carbon going clockwise, and then our CH2OH group is pointed up. And we can place this OH either that way or that way, it doesn't make any difference. But this is the Haworth projection for our beta ribofuranose. So you can see that the furanose pattern, we start with the same template, this 5-membered ring, and then depending on which structure we're looking at, whether it's ribo or something else, we'll have different kinds of configurations at C2, C3, and C4 in terms of where the OH groups and the CH2OH go. So to close this, I wanted to give you a sense for how much of this D-ribose in its open chain form exists once equilibrium sets up. So we can actually work this out using techniques like NMR, and we find that there's only 0.1% of all of the ribose is in its open chain form. About 24% is in the mixture of beta and alpha furanoses. So 24% mix of alpha and beta furanoses. And the rest is actually a pyranose form. So that's about 76%, roughly, right? These are kind of estimates. So you can see that, and this is true for almost all sugars, that the open chain form exists in vanishingly small quantities, but there's this dynamic equilibrium. So even if we were able to somehow take ribose and get just the open chain form, as soon as we dissolved it in water, all of these reactions start, these additions of alcohols to carbonyls, to actually give rise to these cyclic structures. So